Ladies and gentlemen, let me start by saying that I'm very glad that I had the opportunity to talk here about the selectivity problems with number of alloys. I do it with great pleasure also when being on a chain. I was grateful to organizing committee that they wanted to hear talk on something what probably many scientific and industrial managers would tend to declare as being closed. These managers are, of course, the spiritual brothers of those who declared superconductivity 3 years ago as completely uninteresting, and of those who closed the last working electrochemical group in December of the last year. The catalysts which are now working are working very well, that's true. They have an outstanding stability, but for science there is still quite a space, quite room for study. We, I think, are not completely sure what is the exact active site in reforming by catalysts like platinum rhenium. We know that both sulfur and carbon can cause a poisoning effect, but there is not much known how they are different or how much they are similar. And of course, it's a special interesting question is how different catalysts like platinum iridium or platinum rhenium, which both do very good jobs, how far they are similar or how far they are different. I will be talking about catalysts which have been prepared either on alumina or on silica by classical impregnation method under standard conditions, but without ambition to investigate this step in more details. What we did was that we paid attention to the characterization of the catalyst to get some information whether we can really think that we work with alloys and not only with separated metal bimetallics. The platinum iridium catalysts were prepared at such concentration, 5% of metal, that we could do X-ray diffraction, and we saw that these alloys had a lattice constant which was exactly the tabulated value. With platinum cobalt, we saw a continuous change in the lattice constant. Also, there is always some cobalt missing in the metallic form, and cobalt is missing is there in an ionic unreduced form. Therefore, we use carbon monoxide adsorption and carbon monoxide infrared spectra to see that this part of cobalt is most likely not in the surface, but in the bulk of the carrier. The influence of both metals on each other during the preparation is in all cases seen by temperature program reduction and particle size measured in almost all cases by electron microscope. Catalytic experiment which I'm going to present here has been done at 1 atmosphere total pressure with hexane as a model molecule, and ratio with hydrogen, which are indicated here. We got some very valuable information from model molecules like neohexane, but this is what I will not which I will not report today. Catalysts were compared in a sulfur-free state and in a state when the catalysts were sulfided. Sulfidation has been performed by introducing thiophene at 300 degrees C, and then for several hours, and then several hours reduction in the same apparatus at 400. Then the catalysts were reduced again in C2 at 450 centigrade. This neohexane, with N-hexane, couple of reactions are possible. First, you can cut the molecule by hydrogenolytic splitting, and again, metals which have been investigated differ in a characteristic way in the following sense. Platinum is very good in iridium in splitting molecule in the middle of the molecule in an inner splitting, while, for example, rhenium is much better in splitting molecule in many methane molecules at the same time, or in the terminal splitting. The same holds for cobalt. There is also isomerization on metallic function at low temperatures, which survives to higher temperatures, and there is dehydrocyclization reaction. It comprises, in our case, all these products. Also, at the low temperature, methyl cyclopentane is also more populated than benzene. Let us go slowly through this slide, which shows the data for the 3 studied systems on catalysts which are sulfur-free. When we compare platinum with all 3 added metals, then all 3 added metals are excellent hydrogenolysis catalysts as compared with platinum. Therefore, it doesn't surprise, and it had to be expected, that when we go from platinum to the other metal, cobalt in this case, iridium in this case, or rhenium in this case, we go over from platinum behavior to the behavior of the other metals. Like hydrogenolysis goes up, goes isomerization in green down. In these 2 cases, there is no curve for dehydrocyclization because it follows approximately the curve for the isomerization, and I didn't want to make the sheet too busy. The situation changes quite dramatically when we go to the sulfur content. Once more, the sulfur-free, its hydrogenolysis going up, isomerization going down. When the catalysts are pre-sulfided, First, of course, the activity falls down quite dramatically, but the decrease in activity is not the same relatively for all catalysts. This platinum iridium is the smallest, with platinum cobalt is the largest. This is not very surprising, because this is also the sequence of the increasing, in this way, increasing strength of the metal-sulfur bond. What is more interesting is that in all cases the isomerization is increasing, and hydrogenolysis is, in these two cases, clearly decreasing. When we worked with neohexane, there is only one product which can be formed by carbenium ion reaction, and it is 2,3-dimethyl butane. Means that one CH group is shifted in neohexane to the neighboring carbon atom. And on sulfided catalysts, this was the only product which we could see. So, of course, we started to suspect that what is being seen is that while on sulfur-free catalysts, the acidic part of the bifunctional mechanism is almost absent or is not important compared with the high activity of the metal. On the sulfided catalysts, it was different. This platinum rhenium was also important, that when we put platinum rhenium on silica instead of on alumina, then before sulfurization the catalysts were practically the same, but after sulfurization there was no activity with silica supported catalysts. Then we made experiments in which we dosed increasing number of pyridine molecules. It was pyridine, this is milliliter pyridine at saturated pressure of pyridine. And you see that from all reactions the isomerization is decreasing most. And hydrogenolysis and dehydrocyclization, which at these temperatures are more metal function products, are much less effective. When we stopped the dosage of pyridine, then dehydrocyclization and hydrogenolysis very slightly increased, and when we set in a regeneration cycle by hydrogen, they went again slightly up. This led us to the conclusion that what we saw with this platinum rhenium and other catalysts was a shift from metallic function to the acidic function. This platinum cobalt, it was very much the same, only there was practically complete irreversibility in the behavior with regard to pyridine. In this sequence, platinum iridium was different. First, platinum iridium on silica, even when sulfided, remained active. Second, again we saw that the isomerization is influenced most from all reactions, but when you stop dosing pyridine, the change is very much reversible. And when we compare the platinum iridium catalyst on alumina and on silica, we see a small difference. On platinum, iridium, on alumina, there is a little bit higher isomerization, but after pyridine treatment, these two systems are equal. So this has led us to the conclusion that with platinum iridium, it is mainly the metallic function which is observed, and that the slight increase in isomerization is to some extent to be partial extent to be ascribed to the modification of platinum surface by iridium and by sulfur. Effect of carbon is again very important in the industrial practice, and the question is whether it is similar or equal to the effect of sulfur or not. On the first glance, there is quite a high similarity. We apply pyridine, we see again that the effect of pyridine is to a high extent reversible. And when we regenerate by hydrogen, we go back to the original values of high hydrogenolysis and lower isomerization. It means that there is some similarity, at least in that respect, that isomerization is promoted by the presence of carbon, but it is not now the acidic isomerization which we saw with sulfur. We came to the conclusion, which is at the moment as valid, as nice as this sheet. With three different additives, we see a different contribution of the metallic and acidic function. The lowest contribution of acidic function is on platinum and iridium. The highest on platinum cobalt, platinum rhenium is somewhere in between. Conclusion are ones here. Cobalt and rhenium are very near to each other, and they show a very similar effect in clean state, sulfur-free, or in sulfide catalysis. In cobalt and rhenium, we see a clear shift from the percentage in the total reaction, which is supplied by the acid catalyzed reaction. With platinum iridium, the metal function is slightly modified by sulfur, but it remains important also after sulfurization. Those who follow the literature on this subject will remember the paper which the Shell group with Wolfgang Sachtiel published on platinum rhenium, in which they suggested that the high isomerization with platinum rhenium catalyst is mainly caused by the fact that platinum surface is divided into smaller ensembles by rhenium bearing sulfur on its top. With our experience, we would say that this model probably holds mainly from platinum iridium, but with platinum rhenium, it is the shift from the metallic to acidic reactions which reverse. And the effect of poisoning by sulfur and carbon is indeed to some extent similar, but again, with carbon it's more the modification of the metal than modification and increase of the activity of the acidic site. Thank you for your attention.
The paper is open for discussion. Yes, again.
Gilly Fisher, General Motors. At least in the case of the sulfided platinum iridium, I believe in the first isomerization reaction you talked about, you got a synergistic effect where you had a higher rate in the middle of the alloy than at the ends. Were there any consistent patterns of that sort of behavior?
It was selectivity which I showed.
I'm sorry, the selectivity was enhanced over the... Are there any patterns to that sort of behavior?
I cannot tell you more than there was in the slide, because both platinum and iridium show in this particle size very similar pattern of cracking. So I cannot say what is in this increased cracking which you notice, whether it is from platinum being promoted by iridium or vice versa.
So it's not an ensemble size.
I don't know.
May I ask a question in connection to that? When we studied the unsulfided platinum rhenium, we found at Campbell before us in the turnover frequency a volcano-shaped curve. You didn't show yield curves or turnover frequencies, you showed only selectivities.
We find too.
Okay. The last question, yeah?
You didn't mention what pressure you were operating at.
1 atmosphere, total pressure.
Don't you get pretty fast aging there, so that are your results, instantaneous, or do you think they're...
No, it is a slow deactivation, but most of the data were measured under increasing and then again decreasing temperature sequence of measurements, and there is, with most of the catalysts, very little difference. There is some difference, but not which would change the principal picture.
Okay. Thank you very much.